Hello friends and welcome to Geeks for Geeks. In this video, we'll see the problem to find median in a row-wise sorted matrix. Problem statement: given a row-wise sorted matrix of size R cross C, we have to find median of this matrix. Row-wise sorted matrix is a matrix in which every row is sorted. R cross C is always odd here. For example, consider this matrix of size 5 cross 3, that is of size 15, which is odd. Each row of this matrix is sorted. If we have to find the median of this matrix, we consider putting all the elements of this matrix in an array and sort that array. So median for the sorted form can be easily found to be middle element of this. So we conclude that the median for this matrix is 6. Naive method to solve this problem is to store all the elements of the given matrix in an array of size R cross C. Then to sort the array, now simply the median is given by array of index R cross C by 2. Time complexity for this method would be: the first step takes big O of R cross C time, then the next step to sort the array would take big O of R cross C into log of R cross C time, because the array size is R cross C, and finding the median is just big O of 1 time, that is accessing the R cross C by 2 index element of array. So overall the time complexity for this method is big O of R cross C into log of R cross C. Space complexity for this problem is big O of R into C, because we are taking an extra array of size R into C. Because the naive approach takes lots of time, an efficient approach to solve this problem is using binary search. Since every row of the matrix is sorted, the idea is to use binary search. We should note that for a number to be median, there should be exactly n by 2 numbers which are less than this number. The idea is to use this fact. N is the size of list of numbers. Algorithm for the efficient approach is: we start by finding the minimum and maximum element in the matrix. Minimum element can be easily found by comparing the first element of each row, and maximum element can be found by comparing last element of each row. This is because the matrix is row-wise sorted. For example, consider a case where minimum and maximum comes out to be 2 and 8 respectively. Now we perform binary search on the range of numbers from minimum to maximum. The range of numbers from minimum to maximum is 2, 3, 4, 5, 6, 7, 8. This is the whole range. We perform binary search on this range, that is finding the mid of min and max, then getting the count of numbers in the matrix that are less than our mid, and then accordingly we change our min and max. If the count of numbers which are less than or equals to mid, if this count comes less than R cross C plus 1 by 2, this means the median is definitely greater than mid, so we update min to mid plus 1. Otherwise, if count is greater than or equals to R cross 1 by 2, then simply our median can be less than or equals to mid, so we update max to mid. Coming on to the code for this problem, the binary median function takes as input the matrix and the number of rows and columns in it, and returns the median of this matrix. We start by finding the min and max element of this matrix. We run a loop for each row, and then min is updated to the minimum value in the leftmost column, and max is found by comparing the maximum element in the rightmost column. We take a variable desired and initialize it to r cross c plus 1 by 2. This value represents the index of median if the matrix is put in array format. Now we run a loop for the range of numbers from min to max. While min is less than max, we find mid equals to min plus max minus min by 2. We do not directly do mid plus max by 2 to prevent any overflow, and then take a variable place equals to 0. Place will store the number of elements in the matrix which are less than equals to mid. To find the value of place, we run a loop for each row. For example, if this is our matrix, then this loop runs for each row. Now for a given row, consider say this row. For a given row, place is updated to place plus upper bound for that initial and end iterator for that row, comma mid, minus m of I, the initial iterator of that row. This whole expression helps find the number of elements which are less than equals to mid in that particular row. We are able to use the upper bound function for that row because the row or that array is sorted. The upper bound function takes as input the start and end iterator of an array or a vector and takes a value and returns iterator to first greater element then value. And if we subtract the initial iterator from that upper bound function, this will help us find the number of elements less than equals to the given value. Now when we find the place, if place is less than desired, we update min to mid plus 1, otherwise max becomes mid, as we discussed earlier. When this loop terminates, we come out of the loop and return min, because at last min stores the median of the matrix. Coming on to time complexity for this code, this first loop takes big O of R time, then inside the second loop, these initial steps take big O of 1 time, then there is a loop for R times, and in each iteration there is an upper bound function on an array of size C. So overall the time complexity for this would be big O of R into log C, because the time complexity for upper bound function is log of size of array, and then these steps take big O of 1 time. So overall all these steps take big O of R into log C time. Now we have to see for how many iteration does this loop run. In the worst case, we see that the numbers will be at max of 32 bit. An integer is at most of 32 bit. So the binary search of numbers from min to max will be performed for at most log 2 of 2 to the power 32. 2 to the power 32 is the maximum range possible. So if we run performing that binary search on the worst case, that is a maximum range of numbers, time complexity of log 2 to the power 32, that is 32. So at most this loop will run for 32 times. So in worst case, time complexity would be big O of 32 into R into log C. Auxiliary space is big O of 1. To understand this code better, we consider an example. Consider this row wise sorted matrix of size 3 cross 3. Consider the initial variables that are min, max, mid, place and desired. Min is the minimum from the first column, that is 1, and max would be 9. Now we come to this portion of code. Desired is given by R cross C plus 1 by 2. So desired is made 5, that is 9 plus 1 by 2, which is 5, while min is less than max. Since 1 is less than 9, we move inside the loop and update min to this value. Mid becomes 5 and place becomes 0. Now this loop will help find the number of elements which are less than or equals to mid in this matrix. The number of elements less than equals to 5 in the first row are 2, in the first row are 3, in the second row is 1, and the third row are 1. So total number of elements less than equal to 5 in this whole matrix is 5. Place is updated to 5. Now since place is greater than equals to desired, so max is updated to mid. Now min is again less than max. We move inside the loop and update mid to 3 and place is made 0. Now finding the number of elements less than equals to mid in this matrix, less than equals to 3. So in the first row there are 2, in the second row there are 1 element less than equals to 3, and in the third row there are 3 elements, 1 element less than equals to 3. So in total place would become 4. Now place is less than desired, so min becomes mid plus 1, that is 4. Now again min is max less than max, so mid becomes 4 and place becomes 0. Updating place in a similar manner, place becomes 4. Now place is less than desired, so min will become mid plus 1. Now min is no longer less than max, so we move out of the loop and return min, that is we return 5. So 5 is the median for this matrix. Thank you for watching. Please leave us your likes and comments. Also, do subscribe to our channel by clicking that red button and click the notification bell to receive all the updates from our channel. Thank you.